Welcome to Hot Chips 2025. Tutorial 1. Datacenter Racks.
All right, welcome back. Hope you enjoyed the coffee break. So we're going to go into 3 case studies now. Now that we heard about the actual technologies shaping data center rack design, now we're going to go into 3 case studies, deep examining the details that the actual design teams at Nvidia, Google, and Meta had to go through. So first up is John Norton. He's actually going to walk us through the GB200, GB200NVL72 rack design.
All right, thanks a lot, Ralph. Hello, everyone. Thank you for being here. So my name is John Norton. I'm a mechanical engineer at Nvidia. Today I'm going to talk you through this case study of GB200, GB300. As a mechanical engineer, I'm going to focus more on the mechanical and thermal aspects and challenges of the design. So I'll start by introducing you to the MGX Architecture. That's a contribution that Nvidia made to OCP last year. And I'll jump into some of the challenges that solved when we looked at designing GB200, GB300, and then talk a little bit about the specific implementations of the product. So to start off, what is MGX? So MGX is an architecture that Nvidia developed to address the challenges we saw when we looked at scaling accelerated computing across the world. What we found is not just AI or inference workloads, but other workloads when we were designing for those and designing for specific customers, there was always an aspect of the system that we had to tweak just a little bit. Some customers prefer a specific kind of management or a specific network interface controller or NIC. Some use cases require a different mixture of CPUs, GPUs, DPUs, and what we were having to do is continuously reiterate a system to change one small thing, but that one small change would have ripple effects across the whole system. So to address this challenge, we came up with MGX. It's a modular architecture. So we take the system and we cut it up into small pieces, building blocks, modules, if you will. And each of those can interoperate with a different set of modules. And we'd established a kind of common set of specifications and interfaces for those modules to share. What that allowed us to do is do an initial upfront investment on a single infrastructure, a single set of building blocks, and then only have to change one building block at a time as needed. By contributing it to OCP, it became open, it became something that our customers can work within our supply base, and ultimately allowing them to make those small customizations for their preferred implementation, be it a management or NIC, et cetera. You can design that into your own little part of the system. That really addressed one of our biggest challenges, which was time to market. When you keep rebuilding something and reinvesting in something over and over again, you can't move as fast as we wanted to. Having that common infrastructure, it allows us to leverage that initial investment across multiple generations of chips. That's exactly what we're doing now. And then, as I said, by contributing it to OCP, my job's easy. This is my slide from last year when I contributed this to OCP. You can go find this on the OCP website. It became open, flexible, open ecosystem for people to contribute to. I'm going to focus today on 2 aspects of that architecture, the MGX rack infrastructure and then the MGX compute and switch trays. These are the elements of that architecture we put together to build GB200. I should actually point out in the lobby, there is a GB300 compute tray and a GB300 switch tray. So we've got the hoods off of those. You can go take a look under the hood. But I really want you to take away that this is an open set of standards. It's an open specification. We published all the 3D models, 2D drawings, an extremely long spec, and it's all available for download today on OCP. So first I want to set the table a little bit on the GB200-300 system. I'll just walk you through a high-level rack overview. So this picture on the left has the front view of the rack. Picture on the right, that's a rear view of the rack. I'll start at the top, where we, of course, have top-of-rack switches. This is typically your management switches, management connectivity up top. Directly underneath, we have the rack power supplies. So those were talked about a little bit in the previous session. What those do is they bring in the high voltage AC from the data center and then convert it to DC output to the DC bus bar that's in the back of the rack. You can see that in that right-hand picture running up and down the middle. Directly under the power supplies, we have the compute trays. So in GB200, 300, we have 10 compute trays, followed by 9 switch trays, and then another 8 compute trays. Each of those compute trays is capable of 80 FP4 petaflops. The entire system, when we tie it all together with the switches, that's capable of 1.4 exaflops, FP4. The entire system is approximately 120 kilowatts. Each compute tray is around 7 kilowatts. So we tie this all together using NVLink through what we call the NVLink spine. So you can see that in the left-hand side and right-hand side of the back of the rack. That is the NVLink spine. So NVLink runs at 200 gigs per lane. It's a low latency copper interconnect. We've heard a lot of speakers talk already about the benefits of using copper. And so we tie all of those GPU trays together to switch trays using the NVLink spine. So you can see in that picture, we've got the covers removed. You can see the copper cabling running up and down there. So I want to talk about some more detail on the rack. So I mentioned this is contributed to OCP. So that's actually where we started. The MGX rack started life as a ORV3 rack. ORV3 is a open rack standard that was established in Open Compute Project, OCP, and there were a lot of elements of that we really liked. We liked the rear blind made power. That was an existing feature of that rack. And we also liked the serviceability aspects, the front cabling, cold aisle access. You can service most of the rack without ever going into the hot aisle. We saw some challenges though when we tried to just use that whole cloth, which I'll talk about. So one of them was OCP racks, that OCP rack specification just deploys devices on a 48 millimeter pitch. Standard enterprise hardware that's been in production for decades now, that's deployed at a 44.5 millimeter pitch approximately. And that's what's called the 1RU space. Or it's a EIA 19-inch standard. It's got a lot of names. They all mean the same thing. 44.5 millimeter pitch. So what we did is we took those EIA features, we implemented them into the rack, so now we can deploy nodes at a tighter density. This has a meaningful, a lot of benefits I'll talk about in a little more detail later. I mentioned the bus bar. So the bus bar running up down the back of the rack, that was capable of approximately 35 kilowatts, and we needed about 4 times that much. So we created a deeper, larger bus bar, more cross-sectional area of copper to support up to 1400 amps for this system. Now that deeper bus bar actually hung out the back of the rack, along with the manifolds and the NVLink spine, which I'll talk about more. So we created an extension frame that wraps around the back of the rack that takes it from a standard 1068 millimeter footprint to the next size up. That's a 1200 millimeter footprint. So in addition, we needed to support the density, the power density through liquid cooling, and we needed a blind-made set of manifolds to support that. There are other examples of blind-made liquid cooling out there in the industry, but we didn't see anything that met our needs, not just around thermal capacity. You have to drive a lot of fluid flow to support that 120 kilowatt number, but also at that node density, that tighter pitch. So we created a new set of blind mate manifolds to support that. All right, so I want to talk in more detail about those manifolds and about some of the aspects of the rack. So the manifolds here pictured in this image on the left, we're kind of, as we move left to right, we're kind of building the rack up. These are 3D models, again, that are available. So we start with the manifolds. These manifolds actually, they start life as an extruded stainless steel tube. This tube is taller than me. It's 2.1 millimeters tall. The rack itself actually is 2.2. We tried to get one here to put it in the lobby out there, but it wouldn't fit through the door. So we start with this tube, and then we go in and we weld a lot of mechanical mounting points to it, alignment features. The ports for the actual QDs are welded on there. And what happens is when you weld something together, you introduce a lot of heat. That heat actually creates a curve in the manifold, which is meaningful across that very long span. So we take that weldment, that whole assembly, and we put it in a giant CNC machine, really big one. And we worked with our supply chain, we worked with our partners to go scale capacity. We had to go find those machines in the world and scale them to be able to meet our demand. And because of that, we're able to machine in these very high precision features and high precision locations for the QDs themselves, so that once we take this thing and put it in a rack, we can reliably mate the quick disconnects without any dramatic misalignment. So not only is there manufacturing challenges there, but also just some physical challenges. We take that manifold and we position it in the center, and we're very deliberate about that. We position it in the center of the rack off of datums that are centerline of the manifold. The reason for that is the coefficient of thermal expansion of stainless steel is actually pretty large in this scale of things. And with this manifold being 2.1 meters tall, you'll find that going from its ambient temperature of, say, 25 degrees C to its service temperature of around, say, 75 degrees C, there is a meaningful expansion that happens across that manifold, multiple millimeters. Enough so that if you didn't do it right, you could shear mounting bolts. You could end up with QDs that don't mate reliably or jam. And so we pin it in the center, and it cuts down on that thermal expansion in half. We only get half the length that grows, and we're able to manage that. So you also see on the manifolds here, there's quick disconnects that support the full complement of nodes we can put in the rack. Each of those disconnects requires around 40 pounds of mating force. It doesn't sound like a lot if you're talking about a stainless steel tube, but when you stack 48 devices in here and you add it all up, those stainless steel tubes move. They move enough to matter. And so we have to build in support bracing behind the manifolds to kind of support it across that span. Multiple millimeters of deflection otherwise. So speaking of structural support, that middle image is kind of an exploded view. We've got our manifolds in there, but now we have the NVLink spine coming in from the left-hand side, and then on the right-hand side you can see structural braces. The reason for that is the NVLink spine is actually broken up into 4 columns. You can see them pictured there. Each column has a connector that hits every GPU and every switch, and each of those connectors is floating on a spring. It's a spring-loaded mechanism that gives that connector plus or minus 3 millimeters of float in X and Y, 4 millimeters of float in the plug direction. That's very important because when you build anything, you can ask your supplier to make it 100 millimeters long. You'll get it back, it'll be 99.98 millimeters long. That's what we call tolerance. And manufacturing tolerances, they add up, especially in large products like this. So we have to be able to accommodate for that manufacturing variability. And so we float those connectors. That allows them to really get their fine alignment position as the compute trays plug in from the back. You'll see the connectors sticking out the back of the compute tray in the lobby. So they're spring-loaded, they can float, they can reliably mate, but we have to generate enough force to actually plug them together. And that force is substantial. So we add it all up, every one of those connectors, every one of those cable cartridges, every one of those QEDs, we end up with 6,500 pounds of mating force in the middle of that rack in that 27U span. To put that in context, that's more than a lot of cars. I Googled it. It's actually the curb weight of a Chevy Tahoe parked there in the middle of the rack. Forever. It is spring-loaded, and for the entire service life, the rack has to support that weight. If you did that into an off-the-shelf rack, it would simply bow and nothing would work. So we created all of this mechanical structure, did a lot of iterative design, a lot of simulation, and we came up with a structure that's stiff enough to only deflect tenths of a millimeter with that amount of load. So you can see those braces coming out the right-hand side of the rack. Those are actually welded or riveted in place. And then on the left-hand side, we have the cable cartridges coming in. Those are then supported in the rear by that cage of brackets in the back. All in all, we have added 4 cable cartridges, which weigh about 40 pounds apiece. We've added about 80 pounds of steel to reinforce the rack itself and get that front-to-back stiffness that we need. And then you come in with the compute trays and the switch trays, power supplies, etc. This rack can weigh up to about 3,600 pounds. Also difficult to get upstairs, I bet, to get it in here. And so we have to reinforce the rack itself. We actually go in and we change the amount of welding that happens up and down the rack on the uprights. We reinforce the bottom bracket of the rack itself, and we reinforce the wheels so that this thing can be reliably transported, packaged, transported across the world, shock and vibe, etc. All right, so a few more details on the rack. I talked a little bit already about the RU versus OU pitch, 48 millimeters versus 44.5. That had a meaningful meaningful impact on our node density, so we could fit more devices in the same space. But it also means, of course, that things are closer together. So Frank and Darren both talked about the importance of copper connectivity and the challenges associated with that. So NVLink, as I mentioned, is 200 gigs per lane. That is not an easy signaling speed to design around. And so by tightening the pitch and pushing things together, we actually eliminated 120 millimeters out of the cable length. It doesn't sound like a lot. It was about 4 or 5 inches, but that has a very positive, meaningful impact on the signal integrity running through those cables. Every cable has a certain amount of dB per inch. You cut 5 inches out, you've done yourself a favor. So that was one benefit of the RU pitch. The other is that RU devices are also narrower. So you'll hear OCP describe itself as it's a 21-inch environment, referring generically to the width of the tray. EIA or 19-inch standards, 19 inches, a little narrower. That little bit of space per side is actually where we deployed a lot of that structural support that I talked about. So that's deployed inside the rack and eats into some of that width. It's also where we put the blind mate, the latches. So each compute tray requires about 200 pounds of insertion force. Each switch requires 300 pounds. So you need some mechanical advantage in your latching solution in the front there to be able to plug that in. But in addition, by narrowing the device, we actually increased the front aisle cabling space. So I mentioned OCP, ORV3 racks, front cabling, that's great. But what we found is when you mock up a GB200 or a GB300 cabling, when we did this early on, we realized, holy smokes, we're out of space. We can't get these things out. And that's because of all the I/O demands that we see coming out of these servers. We want to do everything in copper. I think a lot of speakers have already talked about that. Save money, save better reliability. And copper interconnects, especially as speed goes up, they get fatter. Bigger pipes, less loss. So we have to package more bulk, just cross-sectional area into the front of that rack running up and down. And In this picture on the right, you can see if you do that, you can't take your tray out because you've covered, the cables are literally covering the tray. So going to that 19-inch EIA form factor really helped us solve that problem too. Of course, being in an EIA or being able to support traditional enterprise hardware also allows us to deploy traditional enterprise hardware anywhere in the world. And that actually helps us get time to market. We don't have to customize things that might have to go into the cluster, like off-the-shelf storage servers and things like that. All right, so I'm going to jump over now, talk about the trays a little bit. So this is just a logical block diagram. I'm not going to read it to you. You can go read it. At a high level, each compute tray has 2 CPUs, 4 GPUs. I'm trying to map them for you to the physical implementation in the back there. So that is what we call the HPM, or the host processor module. Each one of those supports 1 Grace CPU, 2 Blackwell GPUs. You can see those in the middle. On the south side in this picture is where all the I/O connectivity comes out. And on the north side, that's our NVLink connectors. So those are the connectors that are poking out the back of the compute tray. So we take these HPMs, we package them up in what we call a micro MGX board form factor, going back to OCP. Again, made my job easy here. So this is straight out of OCP from last year. We created this tray. This is showing the 2 HPMs, 2 board form factors plug into the back there. In the front, we have the cooling zone or the fan zone. We can deploy multiple configurations of fans, different channels, different ingress, egress for cables. And then getting back to the modularity story, in the front of the server there, you can see we've segmented it into a number of sections, 3 in this case. So these are the bays where people can develop their own management solution, develop their own NIC solution, deploy one set of SSDs or another set of SSDs, U.2 or E1S, DCSCM. I'm rattling off all the fun things that people like to put in the front of these trays. As well, we can configure the different I/O needs. Some people want 100 gigabit networking. Some people want 200 gigabit networking. And we can reconfigure the front of that tray while everything behind it stays the same. That's getting back to that multiple generations of leveraging. Gets us faster time to market. So on the back of the tray, you'll see the UQDs. I say UQDs, that's a universal quick disconnect. That's also an OCP standard that we leveraged. We then took that and wrapped a floating mechanism around it. So I talked about how we need the electrical connectors to float and find their final home. The liquid connectors need to do the same thing. So despite all of the high precision machining we did on the manifold, we still need a little bit of movement in radial, axial freedom that we have in that float mechanism for those to find their final position and have a reliable, high quality seal. So we have an inlet on one side, outlet on the other. And then in the center is the IT gear connector. That's also an OCP standard that we leveraged, but we needed more power. I mentioned we had to, the 8 kilowatts per tray. We had to also put that connector on a diet. It used to be 50 to 55 millimeters wide. We got it down to 35. Doesn't sound like a lot, but it is a lot when you're trying to package all of this connectivity out the back of the trays. And that actually matters the most on the switch. So the switch has twice as many NVLink connections as the compute tray. You can see here the switch leverages a lot of the common elements from the compute tray, getting back to that leveraging story. You can see in the front, we've got a modular I/O. We're leveraging chassis, hoods. In the back, the same QDs, same connectors, same handles, and really expanded how much space we have in the back of the switch to do all those connections. You can go take a look at the one out there in the lobby. So you can also notice on the side of the tray, there are some perforations over there where it says UQD float mechanism. Just above that, there's perforations down the side of the tray. That's not something you'd see in a lot of enterprise hardware. The reason for that, I haven't talked a lot about it, but there is air cooling in the system as well. We like to talk about liquid cooling, it's very cool. But there's also a fair amount of power that needs to be air cooled in the system. And when you pile up these cable cartridges directly behind your system, you introduce a lot of impedance, a lot of resistance to airflow. And so what we did is we actually perforated the side of the tray, and we perforated the rails that align with the switch tray. And then we perforated the brackets that go around the back of the rack. So we actually created an airflow channel that goes into that space on the sides of the rack and out down the sides of the cable cartridges. This actually had a very positive impact on reducing our fan power, but also our fan noise. And I'm using the switch to illustrate this, and ironically, the switch in the lobby there is a GB200 switch. That switch has no fans. That's one of the changes we made, going from 200 to 300. We wanted to get as much of the power captured into the liquid loop as possible, so we were able to introduce a 100% liquid-cooled switch. So you can go see that back there in the lobby. All right, so what's next? Well, GB200, GB300 is now in full production. It's scaled. It's in multiple hyperscale data centers across the world. I've seen some of them. They're all very cool. Everybody here is going to talk about them. So we like this architecture. We're going to keep implementing it. We're going to keep evolving it. It's open. People can come contribute. We're going to keep pushing the boundaries, of course, of density, power, cooling. And then finally, we've recently announced NVLink Fusion. So NVLink Fusion is an open interconnect that will enable other accelerator providers to design within this open architecture as well. So that's it for me. I think I'm going to turn it over now to William. Thank you very much.
Awesome. Hi, everybody. Thank you for joining us today. My name's William, and I'm going to be talking to you about Meta's Catalina product. I'm joined by Matt, and basically we're going to be walking you through what is Catalina, why are we even doing this, so what is AI at Meta, what motivated us to change from the standard NVLink 72 design, what product we ended up with, so going through the rack level, different components, different technologies that go in there, and some of the supporting technologies. We'll be talking about things like air-assisted liquid cooling, which helps us deploy these racks into some of our older data centers. Matt's going to be joining and giving some more details on server architecture, the different boards that actually go into Meta's version of the Catalina product, and then also a little bit more depth on those supporting technologies that I mentioned. So before I jump into the product, why are we here? Well, Meta is an AI company. We've been deploying AI models for over a decade now, serving workloads like ads and newsfeed, helping users get relevant content that's useful and informative for them. We have basically a history of running these models at scale in our data centers, but we've really seen a big evolution where kind of the number and scales dramatically increased over just the past few years. Looking back in 2022, when we were focused mainly on those kind of traditional ranking and recommendation models, we had clusters that were only around 6,000 GPUs in size, and we were running workloads that only spanned 128 to 512 GPUs. Just 1 year later, as we started to invest in generative AI and things like large language models, we jumped all the way up to 16 to 24,000 GPUs in a single cluster, with workloads running on 16,000 GPUs or more. And this past year, we basically scaled things up even more, where we have workloads running on over 100,000 GPUs in production, and we keep adding more. Why do we do this? Well, Meta is one of the few companies out there where we're unique and we have everything top to bottom in the stack. We have our own models in terms of Llama, like I mentioned, from those large language models. We have our own ranking and recommendation models. We also have our own software infrastructure. We basically have everything in-house, from data storage to kind of job orchestration, everything you need to run your own AI farm. Plus, we also have physical infrastructure, data centers, servers, networking, back-end networks to actually connect all of our users to Facebook's infrastructure. We have everything end-to-end, and basically this is what allows us to develop and deploy these large AI models at scale. Looking forwards, we anticipate these numbers are going to just keep growing. Within the next couple of years, we think this is going to be something that we end up being 10x over the next few years. just driven by some of those things you heard earlier in terms of you really get a lot of benefits as you get larger and larger scale-out domains, and you can have more compute all working towards the same problem. So jumping to Catalina. What is Catalina? It is Meta's version of the NVLink 72 scale-up product. So any of you here who's seen Jensen's keynote at the latest 2025 GTC, you'll know there's a lot of different flavors of this product, the NVL72. Catalina is specifically our version. And going back to our history of kind of contributing back to open source, this is something where we started very early on with Nvidia. We worked with them to help kind of customize the system to our needs and make it essentially able to scale and support some of these large data center environments. And then both of us have actually contributed this back to the open source, where Meta and Nvidia have both contributed both the reference design for the MGX NVL72 rack, and then Meta's contributed our Catalina collateral. It's online on the Open Compute website. People can just go look at it and basically leverage it and use it for your own needs. This is something that Meta does across a lot of spaces. We've done it historically for, again, over a decade. And we work with a ton of different partners, and we really try and help give back to the industry and the community through open sourcing our design, working on kind of technology forums and helping to standardize products and technologies, and giving them back so it kind of helps the industry as a whole. Why did we have to make our own version of Catalina? Well, there's really two reasons: the models and the physical infrastructure. Like I said earlier, Meta is unique where we have everything end to end. We have our own large AI models, frontier models like Llama. We have training, inference, distributed inference. We also have those ranking and recommendation models, which we deploy in large scale, basically to help give users relevant content. This is something where we have to target not just where these models are today when we're starting the development of a server, but obviously the design and deployment takes many years. And this is something that we basically have to work on through the, essentially look at not just where we are today, but also where we're going to be and try and figure out what we're going to be doing. We also have the physical infrastructure, where Meta is unique in that we have our own data centers. And unlike a lot of the other companies in the industry, we don't have things like UPSs at the data center level that basically do power holdup. If you have like an AC outage and you need to flip over to generators, that takes some time. Generators aren't running all the time. And to improve kind of the overall power path efficiency, we basically have an alternative design where we'd use things called BBUs, or battery backup units, that go within each rack. All of this means we can't just necessarily take the standard reference design, but we do try and leverage as many components as we can. And that's where we work with Nvidia to essentially make something that's a good starting point for us to go off and design as we go forward. And before I get into things, so this is the Catalina product. Before I get into things, I do want to just say, like, building something like this takes a huge team. I'm a TPM, Technical Program Manager, and I get to work with people basically spanning across hardware design, validation, manufacturing, compliance, supply chain, data center design, network. All of these people are involved at different stages of the development of this program, and essentially it's a huge effort to lead the end-to-end from design, concept definition, requirements, all the way to deploying it in our data center and getting it to work in our infrastructure. And I think this is one of these things where I'm really excited to be able to talk to you all about this today, because it's a ton of work from a ton of people going into this, and it's, I mean, you know, as you'll see, some of the technologies in here are pretty kind of crazy, and it's awesome to be able to see us launch these sort of things at scale. So jumping into Catalina. This is what we deploy in our data centers. We basically copy and paste these and help scale things out. And this is essentially what we call a pod. So you can see a pod here. One of the main differences from our version of the NVS072 versus the kind of version that's the part of the reference design, we actually have two IT racks that consist of single 72 GPU scale-up domain. Each of these IT racks have the same configuration. They have 18 compute trays split between the top and the bottom of the rack. And they have 9 NV switches within each IT rack on the left and the right. And what you can see here is a big, thick kind of bundling of cables in the middle. This is something that basically allows all of these GPUs across the two racks to basically be combined, connecting through the NV switches to create a single 72 GPU scale-up domain. On the left and right of the racks, you'll see that we have these large kind of ALCs, or air-assisted liquid cooling devices. Like I mentioned earlier, these are basically what allow us to deploy these liquid-cooled, high-power density racks into our existing data centers that we kind of have deployed all over the US and the world, but which were built with basically air cooling in mind. So HALC, you can essentially think of it as it's a giant radiator. You can kind of see all the copper basically going through the rack with a couple pumps at the bottom. And essentially there's fans in the back that basically pass air through. And essentially that cools the liquid, which is then what goes to the rack and actually cools these kind of high power density IT components, so the GPUs, the CPUs, the NV switches. Why do we need two racks? Well, looking at kind of a simplified block diagram of the Nvidia reference design, you can see here they have essentially within each tray, within each board, there's one CPU connected to two B200 GPUs. You have two boards within a tray, 18 trays within a rack, and that gives you kind of the 72 GPU scale-up domain. Meta took a slightly different path. We have a single GPU connected to each Grace CPU, still two boards to a tray. You still have those same kind of back-end networks that are used for the scale out. You have the GPUs connected to the NVLink switches. But now you also have these cross-rack cables that I talked about earlier, where you're basically connecting two identical racks together to essentially provide that 72 GPU scale-up domain. What does that give us? Well, number of GPUs are the same, but it allows us to increase the number of CPUs and the amount of total memory within a rack. So basically going from 17 to 34 TB of kind of CPU-attached LPDDR memory, which helps us get all the way up to 48 TB of total cache coherent memory spent between both the GPUs and the CPUs within a rack. Looking at a little bit more detail at the rack itself, you can see these are the different components we have in there. Like I mentioned earlier, we have power supplies within the racks along with BBUs or battery backup units. These are what take in the 480 volts or 277 volts single phase, and they basically convert it to 48 volts DC, which is distributed through the bus bar in the back, and that's what powers all of the individual kind of server blades, NV switches, and networking devices within the rack. So at the top and bottom of the rack, you can see we have one power shelf, one BBU, and then two more at the bottom of each. We have our fiber patch panel, which is basically what all of the in-rack fiber cabling is connected to for the back-end network, which then goes out to the data center to essentially connect to the networking switches that sit at the end of the row for the scale-out domain. We have our rack management controller, which I'll get into a little bit. Our Wedge 400, which is our front-end network switch. And then we have all those IT and compute and switch trays that I mentioned. So to support this, there's a ton of new technologies that we needed. Some of these are common to all the NVL72 products that John was talking about earlier, like the NVLink switches, the cable cartridges that basically form that scale-up domain, the Grace or ARM CPU, and then also things like the UQD or Universal Quick Disconnect valve that basically let you do that blind mate liquid cooling connection. Unique to Meta, there were a few things we have, like the high power version of our Open Rack V3, so essentially higher powered power supplies and BBUs. We had liquid cooling, so the air-assisted liquid cooling needed to support those racks in traditional data centers. The rack management controller, which is basically a safety and orchestration device that helps kind of enable and disable cooling and also does monitoring for leaks in the racks. We have our network topology, the disaggregated scheduled fabric, which is basically what allows us to connect multiple of these pods together to make larger clusters. And then we have our data center secure control module, which Matt will be talking about in more detail, but basically does things like the out-of-band management within the host. Jumping to the rack itself, you can see here, circled in green, are those power components that I talked about earlier. This is kind of the first deployment of our high-powered rack version of OpenRack v3. And one of the things I always find interesting is that OpenRack v3 was actually first launched with things like more traditional storage and compute platforms in mind. So basically, just as we've increased the amount of power that we have in a rack to support these kind of more dense AI systems, you can see what this means in practice. Like the thickness of the copper on the bus bars, dramatically bigger from kind of our lower power OpenRack v3 original on the left. Then we kind of increase things with a 600 amp bus bar. And now we're all the way up to a 94 kilowatt bus bar in the back of the rack. Looking here, this is the back of the rack itself. You can see within the middle of the rack vertically is that bus bar that basically connects all the power supplies to the IT shelves in a single power domain. You can also see we have those cable backplane cartridges, which are where all the cables supporting the NVLink scale-up domain are in. We also have these large black reinforcements, and that's basically what kind of pushes back on the IT servers against that 6,000 pounds of force that John was mentioning earlier to prevent things from just kind of blowing out the back of the rack. On the liquid cooling front, Like I mentioned, we support both traditional air-cooled facilities through the use of the AALCs. We also support newer buildings that have facility liquid cooling that actually let you just run liquid straight to the rack. And that essentially, when you're actually doing a deployment, you'd see only the 2 middle IT racks. You wouldn't see the AALCs on each side, so a pod is now only 2 instead of 6 racks. To manage liquid, we have something called the RMC, or the Rack Management Controller. Like I mentioned, it sits within the rack, and it basically is constantly monitoring a number of different components within the rack for leaks. It's safely at the top of the rack here, essentially to make sure that if there is a leak, the leak doesn't happen to drip on it and shut it off. But it's basically what connects to the ALCs, tells them to shut off, or connects to what we call the valve train at the facility level, which basically shuts the valves off from the liquid coming in from the building if there are issues. Well, why do we need to do this? I mean, I'm guessing people here can make the assumption, but anytime you're dealing with liquid and a lot of power within a rack, you need to make sure that you're being safe. So we have basically different sensors all the way through the rack, like I said, at all the tray, component, rack, and floor levels. And we spend a lot of time trying to make all these components as reliable as possible. But anytime you're dealing with the law of large numbers and you deploy a ton of these systems at scale, you are going to have issues, and so you do need to make sure you are ready to handle them. We could always just immediately shut off the power the minute we detect any sort of small leak. But that's basically what this picture here shows, is that if you shut off the power, the rack's basically completely off until somebody goes to the rack in the data center with a stick, flips all the breakers off, and then flips them back on to reset it. And so we essentially have kind of a trade-off where we know where the different sensors are. Some correspond to basically really small leaks or maybe just residual liquid that could be left in from manufacturing. And in those cases, we maybe just shut off the sled, or we shut off kind of a couple of components versus shutting off the whole rack. But obviously, if you do have a bigger leak, you want to make sure you're being safe and everything goes off. Again, now we go from the pod to the whole cluster level. This is where Meta has our disaggregated scheduled fabric. This allows us to connect multiple pods together within a single data center, building, or suite. Lets us connect multiple buildings together, and maybe even go larger than that to basically provide these really large-scale clusters. This is something that we've designed in-house. It's tuned for AI, and it helps provide flexibility and speed to basically ensure that we can have multiple AI workloads all running and basically being able to use clusters for, again, some of those different types of models that we have in-house ourselves. Physically, it uses network racks, basically located at the end of each row, that the Catalina connects to for the back-end network. Now, what does that look like in practice? Well, you might have noticed there's a ton of yellow cables within the rack. They basically connect to 3 different networks. We have our front-end network, or north-south network. So this is essentially how the servers communicate with the rest of the services in our data center for things like getting storage to help facilitate model training or communicating with the schedulers. These are connected to NICs on each of the CPUs, and those connect basically, that's kind of the yellow-orange paths you can see here, which connect to the 2 wedge 400s, one at the top, one at the bottom of the rack, and then that connects outwards to the rest of our network. We have the back-end network, or east-west scale-out domain. This is essentially how all the GPUs talk to each other. That's all the blue cabling you can see here, which goes to the fiber patch panel. The rack lands in the data center. Those things are already installed, and the data center networking technicians basically connect the cables at the building level to the patch panel on the top, and that's how they communicate out. And then we also have our management and console network. That's kind of the thick bundle of Cat6 cables you can see on the side of each rack here. This is for things like serial console and basically how configuring switches before the rack is, or the network is actually up and ready. So all of these cables exist on both racks, but I've only drawn them on one or the other just to kind of help simplify things. So that's a high level of what Catalina looks like as a product. I'm going to hand it over to Matt for a little bit more information on the hardware architecture.
Nice. Hello, good morning. My name is Matt Bowman. I'm a hardware engineer at Meta. I design, bring up, and debug our AI hardware. And I am very happy today to be here and talk more about our Catalina system. Both John and William covered this pretty good, but the inputs to our Catalina of what kind of drove it and what we were doing, first off was the MGX Nvidia reference. The nature they designed it being modular, it was great. We wanted to take it. We too like to move fast. That was our starting point. We had a number of unique use cases that also needed to feed into it. As William covered, we have a different ratio of, say, GPU, CPUs, so that was part of it. And then within Meta, our infrastructure, we're all in on the Open Compute project, kind of top down, nuts to bolts. You'll see it across everything they do on all the pictures. You'll see the little OCP green touch points, the methodology of how we do the management, the link sensing, the link control. It was a wonderful example of just a collaboration to get in, get stuff done, build it quick. This is a top view of the compute tray itself. Few things I wanted to highlight is it is a hybrid cooled tray. So on the right side, where you see the rear of the tray, the host processor modules, the HPMs, those are the GB200 modules. They're below the cold plate loop, the liquid cooling, along with the CX7 mezzanine. So we have our backend network, the GPU and the CPU are cooled by liquid. On the front of the tray is where our customization took place. So in this example, the PDB, or the power distribution board, that had some major updates to support what our infrastructure expects on how the power turns on, how we keep stuff alive. We also make use of the DCSCM. It's a very standardized industry component that we use within our trays, within our various hardwares. We also have a front I/O board, which is kind of an underwhelming name, but it's the connectivity to go from our tray up to the RMC. That was a new customization we had to make to support it and deploy this hardware at scale. If I go to the block diagram itself, there's a few examples here. You'll see that there are two trays, and one thing that I want to emphasize is the two trays, each tray has one GPU, one CPU, but we have that red line in the middle, that's the C-Link cable. That actually makes it a unified memory space. There's one operating system that's running within the tray. So it actually is a 2+2 config, just on two separate physical HPMs. We have the boot drive as one of the front accessible E1.S drives. It's partitioned, it's half data, half boot drive. Remaining are used as data drives. And then another very OCP meta-centric infrastructure is we make use of what's called the NCSI connection from the OCP NIC to our BMC. This has a lot of advantages within our rack and our management that we can combine and reduce the number of cables in the system. It already has a lot of cables. Getting fewer cables is definitely an advantage. This is a breakdown of the per board, both NVIDIA reference and then our implementation. We make what we call a TLDR, too long didn't read, so really the summary is at the bottom, but I wanted to highlight the specific boards and kind of what was driving these changes. So I'll start with the last one. The BMC is on the DCSCM. This is a OCP standard. It's a pluggable form factor with the BMC on it. That provides us our management. It's looking at the fans, you have the out-of-band OOB access, you see the sensors, all of the control of the rack. We've standardized on this and we're using it throughout our hardware. So for us, we wanted to use a DCSCM. We also make use of OCP NICs, another OCP standard. Instead of a PCIe Chem form factor NIC, these are front accessible, serviceable, pluggable cards that provide us our front-end network connectivity. Our link with methodology and how we report and handle leaks. So we had the picture of like RMC and the rack level shutdown. We needed that connectivity, so that drove the need to add and incorporate a front panel connection to have the compute tray talk to the RMC. And then finally, one of the most substantial changes is we needed a different standby power of how we're delivering power to both the HPMs and everything else in the tray, so that when there is an event, when we do an AC cycle, a DC cycle, we're standardized in how we handle those events. It's a perfect segue into the PDB. So I wanted to give more of a detailed breakdown. This is our real PDB hardware, kind of a picture of it, of what it's doing, why it's doing it, and what it looks like. If we start at the purple box towards the top middle, that is the cable that's getting you from the bus bar clip to the PDB. So that's the 48 volts. It travels on this kind of flexible, very thick cable, plugs in. The PDB, one of its main jobs is to distribute power throughout the tray. It takes the 48 volts, makes it 12. That 12 is our primary distributed voltage within the tray. So it fed to the HPMs, fed to the fans, everything else. To get the high power, the HPMs themselves are the highest powered components within the tray. We use a rigid bus bar. You can see down in the green box, middle of the board, these are rigid, thick bus bars that you go in, you clamp, correct torque. That gets us the successful power delivery and meets the PDN requirement delivery. Also within the tray, we have very granular and fast-acting leak detection. So leak detection at a physical implementation level, you have these rope sensors, and you connect them in, and they are sensitive to liquid, and they change the resistance. So you connect them, they'll have a given resistance, you get them wet, the resistance changes. That signal processing to do that detection of is the cable getting wet, that is done on the PDB, and we also have a management and control CPLD. That is used to both report and quickly act if there is a leak within the tray. It's tightly coupled to the power, and so if you have an appropriate or catastrophic leak, it can very quickly shut down the tray with safety in mind. Important to that is we have the front I/O connection to the RMC. It's not enough just to shut down the tray, but if the pump remains on, you have a leak and you just keep making it worse. So that was another required connection that we're handling here, all very localized in the board, that a leak happens, you can quickly turn down and also report and say, please turn off the pump and start making it worse. We do have the cable guides, which are in the yellow boxes. So this particular PDB is air-cooled. It's in the front part of the tray, behind the fans, it's cooled. Usually for air cooling, you want nice, tidy cable bundles to keep the airflow clean. Even in liquid cooling, it's still important, because the liquid itself, if there is an event, it may spray, it may contaminate other things. The material or the liquid we use, it's PG25, it's UV fluorescent. You want to be able to have easy, quick visibility into the tray. If you have something that you suspect may have a leak, you pop off the lid, you use a UV light, you check it out. So you want to be able to see, you don't want the spaghetti cables everywhere. Finally, this operates as kind of a jumping off point on I/O, like for our DCSCM. It is panel mounted, connected to the front of the system. We use a 4C plus cable that goes from there to this board, and then it breaks out to the appropriate remaining management connections of the system. Looking at the power block diagram for the tray, we have the notion of an AC cycle and a DC cycle. AC cycle is a complete misnomer. There is no AC routed to the tray. It's just a legacy term that we've continued to bring forward. This represents the heavy hammer, a very common remediation where basically something's not working. Let me completely cycle everything in the tray, including the management. If you hit and do an AC cycle, everything goes down, everything comes back. DC cycle is much more targeted, where only the host side of it gets cycled while the management portion stays up. We have this dedicated branch. If you look at the lower portion of the block diagram below it, there's a dedicated power portion. We do that for reliability. Having your management portion on its own branch means a catastrophic power failure on the high power components is less likely to propagate and cause an issue on your management side. In that branch, we need our front end NICs because we use the NCSI connection that gets us the management. So our front end NICs, the CX7s that plug, those are on the standby power. We have our fans, because the front end NICs do use some nominal power and they are air-cooled, so the fans need to stay on. And then we also have our DCSCM, our management, which, speaking of which, is a good segue. This is our implementation of the DCSCM. So this is an industry standard. You can go in, look at the specification that covers the pinout, the requirements, and all of that. We have to make a number of unique changes to support our infrastructure. One example is the BSM. You'll see it in the outlined red box, and in fact, it's missing. That's by design. That's the boot media for our BMC. Any data that is in our data center that has even a potential risk of contacting user data, it instantly becomes quarantined. It never leaves. It's taken extremely seriously. And so what would happen is if we have a failed DCSCM, and we want to send it for RMA, get it outside the lab, kind of figure out what happened, that BSM needs to be removed, and it will go through some secure erase cycle. It may even get destructively erased if you can't guarantee the secure erase worked, and we call that ERAD, or eradication. We nuke it. And so it needs to be a pluggable component on our DCSCM. Kind of one of the features I'm a big fan of is we do have what's called the OCP debug port on the DCSCM. This is a USB 3 connector that's on the front of the system. So you can see the little green debug box that we have. This breaks out some of the sideband and control signals along with the consoles of the BMC and the host. It makes it where something broke and for whatever reason the network's down, you can't get to it remotely. As long as you have physical access, you can log in, check logs, dump, look at status, try to cycle it, see what's on. But that's really used in the sense of, okay, something's broken, let's figure it out. In that same vein, what we're finding in these larger AI systems with a lot of domino effects or potential domino effects is the need for robust logging. So we have a handful of CPLDs, management CPLDs spread out the system. They're typically doing things like monitoring power rails, looking at temperatures, leak detection. They're tied into all that, so they have a very good low-level view of what's happening. We've implemented what we call a flight data recorder functionality into it, that throughout the life of the CPLD, in its own internal non-volatile flash, it's logging the state machine changes as it's going through. And this has been very helpful when you have these corner case or quick transient events that may happen faster than you could get in the normal logging channels. Our goal is to get it all through the BMC, report it out to the network. But in the case of, for example, a leak where the CPLD may take very quick action to shut things down, you still want that log of what happened and be able to deduce it after the fact. The I2C dump there is just an example. In the red, you can kind of see the transitions of it going through. In this case, it was a faulty leak sensor, in fact. So you could see it erroneously was detecting leak, not leak, and actually seeing over time what was happening was very helpful. The block diagram for the SCM, there's only like 2 or 3 things I want to highlight on here. Is we do have the NCSI connection, so I mentioned that earlier, but we don't have dedicated management cables to each of our trays. You use the data path cable that's plugging into your front end CX7. We pack off the management, and that is our connection OOB, out of band to the BMC. The racks already have a lot going on. It's actually quite nice that we don't have all these extra management cables on it. We also have additional debug features. If you see the LEDs on that picture on the left, where you see the different green LEDs, often if you have a leak, a failure, a power fault, some idea, you need a good first level triage of, is this something I can debug? Do I need to escalate? Do I need to bring it in? Those LEDs are meant for that. So when we covered the PDB earlier, we talked how there's initially 48 volts coming in, then it converts to the 12, and then that feeds to the various management and HPMs. One of those LEDs represents, with no programmable logic involved, it's kind of bare hardware, that if that LED is on, you can be convinced the 48 volts, the bus bar clip, the connection to the PDB is good. So you see that, you quickly know, okay, 48 volts is at least making it into my tray. Another one of those LEDs very quickly represents the output of that 12 volt. If that LED is on, you can confidently say the 12 volt conversion on the PDB is taking place. That is really good. The PDB is buried in the bottom of the tray, and if you have to service it, it's a very high effort, high cost, high risk one, because you have to completely disassemble the tray, put it all back together, something else may go wrong. So you want to have very high confidence that if you say the PDB is broken, you have a very quick way to actually do that, and not just be part swapping to try to fix it. The RMC this is also contributed to OCP. You can go to the OCP work group, the contributions, get the full spec, the detailed collateral. This is used as the orchestrator of our liquid cooling in the rack. So within it, you'll see along many RJ45 connections. Those are repurposed. We wanted something quick, simple, very commodity style RJ45 connections. RMC is connected to each of the compute trays and the NVLink switches. So it was good collaboration, again, with Nvidia to make sure it's compatible. We're talking the same language. But it's used, there's a two-way communication with both GPIO signals along with I2C to say, hey, my power's good, I have a leak, please shut down, along with some extra serial communication. This orchestrates, and it can basically command something in the rack to turn off if it sees something bad going on. This also connects to what is supplying the liquid cooling. So we support both AALCs for some of our data centers. Other data centers, we have facility water that use valve trains. This has connectivity to both of those, in very similar reasons that if there's a leak, you need to stop the pumps. You want to stop the leak from occurring and making it worse. So we have both. And then the RMC itself is connected to rack-level leak sensors. And if I tie it, it's a good segue. We've created different buckets into our leak sensing. And this is our categorization of where they are and where we route and handle those little ropes that are picking up the leaks. Small leaks represent contact points. Usually it's where the QDs would be. The first portion where something may start to dribble, there's some residual liquid. Usually, QDs, the cold plates, it represents kind of connection points where very likely a leak would probably start there if you have some debris in the QD and it starts there. Tray leak are progressively more catastrophic or more severe, perhaps. These are wrapped around the HPM, the cold plate, where a majority of the liquid is flowing. Also within the bottom of the tray, it's snaked, so that if you have a leak that's enough and it's making it to the very bottom of the tray underneath everything, you can be pretty confident there's a notable leak occurring there, and you need to take action. At even a more extreme level would be a rack level leak, where at the manifolds that, for example, John showed those, that has a tremendous amount of pressure, a tremendous amount of liquid. If that's leaking, that's very bad news. You need to take action. We also have a drip pan in the tray. So this represents an overflow event. There's been so much liquid, it's kind of left the tray and it's now getting collected at the bottom of it. And then the ALCs themselves have pumps, they have the radiator. You need to be able to detect and respond to those. We have it mappable. Basically, we have the physical implementation of the sensors, and within the RMC and our compute tray, we can take different actions. The reason we would do this is highly dependent on the specific product and what product phase we're in, the maturity of the product. I had the example of like a faulty breaking leak cable earlier. During MPI, that's more likely. You'll be opening trays, you might be damaging cables, and you generally have people right in front of the hardware. You're not operating them in this abandoned mode. You're sitting, you're debugging it. At that point, you want the leak reported. You may not want to shut down the whole tray or the whole rack. You want to be there, see what's happening, and be able to debug it. As you scale and you end up with more and more hardware and the risk of an unintended system developing a leak, you want to get more conservative. You want to make sure, hey, if there's a leak, we shut down, we keep people safe, we keep material safe. And this is something that we configure in the RMC, we configure in the tray. It almost certainly changes over time and can vary between product. And then just to tie it in, kind of reiterating William's point, William was here presenting, I'm here presenting. We represent just a small slice of the team that works on and gets this deployed within the Meta infrastructure. You see the power, the cooling, the infra, the network, the hardware itself. And I just wanted to reiterate, it is a team effort, and to successfully deploy AI systems at scale, you do have to operate together as one team. So that was my last slide. I'm going to pass it off to Pankaj, but thank you very much.
Thank you, Matt. My name is Pankaj Makhija. I'm a systems architect and a tech lead. I work on TPU products at Google. Today, my talk will be centered around TPU systems and TPU Rack. Yeah, so I'll start off by giving an overview of our TPU systems, primarily all our superpods that we've been launching over the past few generations. And then I will give you an overview of the Ironwood Rack. Ironwood is our next generation TPU product, again, a superpod. And in Google, we use superpod and supercomputer terms interchangeably. I'll also note that there will be an exciting talk on Tuesday where we will be talking about Ironwood SoC, TPU, as well as the system in more detail. And then I'll finish it off by talking about some of the challenges and opportunities that lie ahead of us. All right, so I think there's been a lot of discussions ahead of my talk about the ML machine learning models, how they've evolved over the course of years. The size has increased significantly. To be more specific, the model parameters essentially are increasing the overall size, and then you have mixture experts that also compound the growth of these machine learning models. And what this really leads to is an unprecedented demand for compute flops and the memory capacity and bandwidth, all levels of the memory hierarchy essentially. Scale-up, bandwidth for scale-up network as well as the scale-out network. So all the three fundamental pillars of supercomputing architecture are seeing a very unprecedented demand with the evolution in ML workloads. And this is actually consequentially increasing the system size not only for pre-training our foundational models, but also for inference. And at Google, we look at our current generation workloads as well as what's out there in the future, whatever we can project, to derive our system architecture and system design. And we try to bake in as much as flexibility as possible so that we can instill all the longevity to our products and make them relevant for many years to come. So in this slide, we started off, I'll talk about TPU v4 very briefly, and then move on to Ironwood. TPU v4, I believe we gave a talk on this a couple of years ago. It had 4,096 TPU chips in a superpod. HBM bandwidth was 1.2 terabyte per second per chip, and the capacity was 32 gigabytes. The peak flops per chip were 275 teraflops. And then moving on to TPU v5P, which was announced in 2023, the pod size increased dramatically by roughly more than 2x to 8,960 chips. So did the HBM bandwidth and capacity. So bandwidth went up to 2.8 terabyte per second, and the capacity increased by threefold to 95 gigabytes. And the peak flops per chip increased to about 2-ish range to 59 teraflops. Now moving on to Ironwood, which is our 2025 product, the pod size has increased to 9,216 chips. And the HBM bandwidth has gone up more than 2x to 7.4 terabyte per second. The capacity has gone up by 2x to 192 gigabyte. And the P flops, that has changed or increased by 10x, which is a pretty significant jump to about 4.6 petaflops. I remember roughly about 10 years ago when I was working on my first supercomputer, the entire supercomputer's peak flops were around, I'd say, 8-ish petaflops. So we've seen a dramatic change in overall compute density in our products. And in general, like I mentioned earlier, we look at our current generation and future workload projections to define the architecture. As you all may know, I won't go back as much as Alex did, but the transformer-based models, they've been at the epicenter of AI revolution over the past few years. And if you remember, BERT perhaps was probably one of the first transformer-based models, and it was mostly for natural language processing. And fast forward to 2025, we now have large language models and mixture of experts doing thinking tasks. So again, the workloads will keep on evolving, and at Google we make it strive to essentially have whatever insights we can get from current and future projections to define the architecture so that we can bake in all the flexibility possible and make it more relevant. And let me move on to the next slide. All right, so let's now talk about the Ironwood SuperPod or the supercomputer and how we essentially configure it to support multiple clusters that can span across multiple data center buildings or data center halls. So I already talked about the scaling that Ironwood will be delivering. It's about 1.5x to 10x. I didn't mention earlier that about the scale-up bandwidth, but I'll talk about that briefly too. Starting on the bottom left is our TPU SoC, which is, over here. So I think these images are publicly available. And we have 4 Ironwood SoCs in a single board. This is, of course, the PCBA. There's a lot that goes on into packaging this into a single tray. And here is the rack. This is the Ironwood TPU rack. And there are 16 Ironwood PCBA/trays that get packaged into this single rack. That gives us the 64-chip building block, so to speak. And then we've got the logical view of our scale-up network. The scale-up network is based on our proprietary interface called Interchip Interconnect. So we call it ICI for the acronym. And the scale-up network is what allows us to scale from one building block all the way to 144 building blocks for Ironwood product. And that gives us a scale of 9,216 chips in a single superpod/supercomputer. And this interconnect ICI, which is what we call internally, is used to give us the scalability that we need. So if you look at the aggregate flops in a superpod, they're roughly around 43 exaflops, which is a pretty big number. And through ICI network, we also get a pretty large pool of HBM capacity, shared memory, across these nodes, amounting to about 1.8 petabyte of overall capacity. And this ICI network, which is essentially our scale-up network, you can imagine it's being used for all sorts of collective operations, ranging from model parallelism. You've got data parallelism. You can also use it for data parallelism, pipeline parallelism, expert sharding, and all sorts of evolving modes of parallelisms in a very hybrid manner. Now, moving up the stack to the north-south network, this is our data center scale-out network, which is primarily Ethernet-based. And we use this network to stitch together multiple superpods in a cluster or across multiple clusters within a building or across multiple buildings, data center buildings. And this data center network, scale-out network, is used for things like data parallelism, whether it's hierarchical or non-hierarchical. It's also got auxiliary compute and storage systems attached to it over the network. And these auxiliary compute and storage systems are primarily used for all sorts of offloads and also to enable data set ingestion as well as checkpointing, right? So all this together makes our supercomputer or a gang of supercomputers, enabling a very seamless experience for our end users to use these products year over year. Now, I will mention that these systems, the definition, I already talked about the workloads, how we use our workloads and future projections to define these products. But they are super, very well curated to ensure that our pipelines and the end-to-end stack on the hardware side leaves no bottlenecks, because our goal is to essentially increase productivity. And one way to do that is to enable linear or almost linear scaling when it comes to performance, going to tens of thousands of chips, right? So that's the primary goal. And this doesn't come, it requires a lot of collaboration and a lot of co-architecture, co-design across multiple teams in the hardware organization, the software organization and teams, going from ASIC software all the way to the upper stack, ASIC software, XLA, and all the way to the upper stack, which is called pathways. That's a Google-defined stack. And as well as data center, right? So there's a lot of core design that goes on with our data center teams as well. All right, so now let's talk about the suite of racks that comprise our SuperPod. So I already talked about our Ironwood SoC, the Ironwood PCBA that get packaged into the rack. And we have these 144 racks that go into this Ironwood SuperPod. And then what we have here in the middle section is our optical switch chassis, which is used to enable scale-up ICI across multiple cubes or building blocks in a single SuperPod in a very flexible and configurable manner. And these 144 racks, which give us 9,216 scale, the idea is to essentially use these racks for obviously the large-scale training jobs, but also to enable other fragmented jobs. So the size itself is picked very carefully, and also to have enough holdback capacity to enable faster and higher availability. And then these optical switch chassis get packaged into an OCS rack, and we've got a few of these OCS racks per SuperPod. And then at the bottom, we've got this CDU rack, which is our coolant distribution unit rack, which has got a bunch of MCDUs in it that Jorge talked about in detail in the earlier session. So these are the primary racks that get bundled together to a single SuperPod. I'm not showing the network racks here because I ran out of space, to be honest, but there are a lot of network racks as well. Now, one thing that we should really spend more time and energy towards is to think about the turn-up velocity. I talked about the three fundamental pillars of architecture, compute, memory, network. But turn-up velocity, reliability, power, these are all very critical things in this day and age. Right, so ensuring that we have a conscious effort towards improving performance per watt, not only performance per TCO, but performance per watt, increasing availability, increasing reliability so that our end users can get these systems as early as possible, and of course the turn-up velocity. All these things are super critical in deploying these supercomputers and enabling the productivity that they're really designed to deliver. All right, so with that, I'm going to talk about the Ironwood Rack. So here is an image of, the left side has the image of the rack. Before I go into the details, I'll talk about the logical approach here. So we've been using the 3D Torus for the past 3 or more generations of products. Each logical building block is comprised of a 4x4x4 3D network, and using the ICI interface that I talked about earlier. And this 4x4x4 building block, which is 64 chips or nodes, gets packaged into a single rack here. So like our logical and physical building block is essentially here. Now, within this logical and essentially the physical building block, we've taken a hybrid approach for our interconnects. We've got the PCB traces, right? And we've got the copper passive links through cables. And we've also got the optical links, or optical fiber, that gets connected to the OCS through patch panels. And that, again, gives us the flexibility to configure all sorts of 3D torus slices, whether it's 3D torus or whether it's twisted tori. So it's highly configurable. It gives us all sorts of topology options to the end user. All right, next slide. And here's the image of a rack. Starting at the top, we've got the upper drip pan to detect any liquid wall manifold leakage. And this is something you can think of this as like the top hat. It's essentially the power delivery. We've got 2 power domains, one on the left, one on the right, and it takes in 416 volt AC. And then we've got rectifiers that do the AC-DC conversion for the payload, which is over here. Our rack, as you can perhaps see, it's wider than a typical standard rack, and we've been using this rack form factor for multiple generations, and it's served us pretty well. Like I mentioned earlier, turn-up velocity, reliability, accessibility, serviceability is super, super critical for us, and we realized this many generations ago. And that's why we've kind of stuck with this rack, because it gives our techs plenty of space, techs and manufacturers and assemblers, plenty of space to enable or fully support the front panel accessibility, right? Whether it's cables, manifolds, or servicing trays in and out. And it's a very modular system design, so to speak. Here in the middle, we've got these optical fibers that branch off to each of these shelves. And the gray cables that you see, these are the copper ICI cables, which span essentially mostly around east-west side, and there are some connections that go north and south. And many generations ago, we had also taken like a very bold approach to use liquid cooling. Jorge gave a great talk on that. It was not only for us to enable better thermal conductivity, because back then we already realized that Dennard scaling is over, and we had foreseen and thought about power going up generation over generation, so thermal conductivity was super critical for us, and that's why we chose liquid cooling. But besides that, liquid cooling also helped us to densify our systems as much as possible, which in turn helped us to support these passive copper connections. But again, like our architecture, fundamental architecture is essentially around homogeneous ICI scale-up, which is where we do need these optical fibers, right, that go to the OCSs. We also have the rack monitoring tray for all sorts of telemetry and monitoring. There are a lot of devices that it actually monitors besides rectifiers and the battery backup units. We've got these cable managers, kind of hard to see from here. Left and right, we've got these cable managers that kind of help with improved cable dressing. As you can see, the cable and connections and manifolds are quite dense. So we need to pay special attention to all these cable managers and the pre-assembly work that goes on to enabling very smoother turn-up at the data center floor. I talked about the optical fibers and cables, and then again, these are the battery backup units. And like I mentioned earlier, we have 2 power domains, independent power domains, that enable more than 100 kilowatt in a single rack. Let's see, so okay, the other thing I wanted to mention here is the TPU trays. Again, sorry, it's a little hard to see, but where you see a lot of gray copper cables, those are the TPU trays essentially. And they get cabled to our host, or I should say the header tray, which is our server. And we've got like these 4 PCI cables, which are Gen 5 by 16 interface that connect to our header over here. And these blue cables are the PCI cables, right? Now let's talk about the fiber bundles. Like I mentioned earlier, these fiber bundles get used, and you can see the amount of fiber bundles that we have on the cable tray above the rack. All these things, they get pre-deployed, and logically you can think of them, the connections from each rack going to 3 segments because it's a 3D torus network. So we've got the X dimension, Y dimension, and Z dimension. And each rack essentially connects to the respective XYZ partitions. And again, these fiber bundles are pre-deployed. The rack itself, the cabling and everything is pre-configured at our contract manufacturer, and then we essentially populate our host trays and TPU trays on the data center floor and do the QD connections with the rack manifolds. All right, so this is a high-level view of our layout. So on the left, you've got these racks spanning the aisle, and here I think you can maybe barely see, it's probably the CDU rack over here. And here's like the 2D rendering where you can see how does the layout come to fruition on the actual data center floor. Now these CDU to payload rack attach rates, they change. And we have the flexibility to support all sorts of attach rates. And then I think here, it's probably our OCS, one of the OCS racks. And CDU rack and the UPS rack that is needed for the CDU to give us the high availability. And power management is super critical too for us. Like we already have power management, throttling, and other sorts of capabilities on the TPU, as well as the TPU tray. But we've also introduced rack level capping. Not only with the primary goal to support not only the baseline TDP, but also to burst to a higher TDP range in 100 millisecond or less timescale. And yeah, it can be quite useful. So for some of the heavy compute workloads that may need higher burst, flops or the associated power. And there's a very tight hardware control loop that enables all sorts of power capping, whether it's a tray level or whether it's rack level. And we also have data center level power management because, like I mentioned earlier, power efficiency is super critical in this day and age, and we've been working on this sort of architecture, data center level architecture, for quite some time now. The other thing I'll mention is that we talk about TDP, but in general, the systems get deployed at a different provision power, which is kind of based on the average or typical power that we see. And there's, again, a lot of flexibility built into the architecture to adjust things, whether it's at the deployment level or at the software level or any other, upper stacks of the product. And this is just a high-level sort of the sketch to show how these things, the rack level capability, power capability, how it works, and what the time scales are for baseline TDP, which can be more than 100 milliseconds. And then we've got this high TDP mode, which can give us the burst, the power needed for perhaps bursty compute workloads, but at 100 millisecond or less time scale. All right, so I talked about the architecture and I spent some time on the design and also gave you some preview about how we manage these things. But obviously there are challenges ahead of us, right? So, whether it's power, essentially with the end of Dennard scaling, every gen over gen product, we see a dramatic increase in the power. So how do we manage that from the rack all the way to the data center level? And then there is, I think you've seen maybe a couple of more presentations today talking about front panel accessibility, right? So the cabling, the dense cabling on the front panel it's quite congested. And with the rapid growth in our I/O requirements, which may or may not, which may perhaps supersede the growth in the SerDes, right? From technology perspective, how do we make sure we've got the right level of flexibility baked in to our design to enable this high I/O demand, gen over gen? And then the power swings under synchronous training. This is a pretty hot topic, right? At Google, we published a blog where we show that for certain jobs that are clusters, spanning a cluster or multiple clusters, we can see a swing of about 15 megawatt. It's a pretty large number. The superpod that I talked about earlier, the Ironwood superpod, that's about 10 megawatt. So the swing itself is 15 megawatt and can keep on increasing, right, unless we do something about it. And there are multiple ways to approach this, and this is where we perhaps need a tighter collaboration across the industry, right? It's one way to approach this is through perhaps the compiler level to smoothen out power fluctuations, or I should say power profile and chip level subsystem utilization rates. And then there's also impact that can be seen perhaps at the grid level equipment, thermal interface. How do we design these products to support these high fluctuations while also trying to reduce these fluctuations as much as possible by perhaps smoothing up or down the ramp rates, right? And in the cyclical synchronous batch training operations. And then, there are these ML rack standards where I think there is a strong opportunity for us to collaborate together. We have a lot of experience with wider and heavier rack, and also optical connections, right? So I think this is another space where we see a strong potential opportunity across the industry. And essentially share best practices for ML rack deployment and co-design with the data centers, especially when these products land at third-party data centers like Colo, right? So I think with that, I will conclude my presentation. Thank you so much for listening into it.
All right, thank you, Pankaj.
Thank you.
We have time for questions before we break for lunch. While you line up over here, maybe we can go to the online questions first.
All right, certainly. We'll start with one from Meta. This came from a lot of people and might not be something you're going to address today, but everybody wants to know why you changed the ratio of the CPUs to GPUs on your cards specifically.
I think this is something I'm not going to be able to go into a ton of detail on. It really goes back to kind of some of the points I made earlier around we have a pretty big set of workloads that we support across generative AI, looking again at those kind of frontier models. And it's something where, again, this is really one of the benefits we have in terms of we are able to work with kind of the AI researchers and understand what their requirements are, what they think kind of the capabilities they might be needing over the next few years. And so essentially it just goes back to, with those conversations, kind of Obviously, more resources are better, and so having more memory, more CPU within a scale-up domain is essentially kind of the decision we ended up making to basically look at both where we are now and where we think they'll want to be in the next few years.
Why don't you take one more question, Alex?
Certainly. This one is for John Norton. This was asked by people from TCOM and a few other places. Could you comment on the cluster reference architecture for the GB200-300? Are these meant to be turnkey solutions, or do they require additional guidance for deploying?
Probably not the best person to answer that. I know we have reference designs published through a variety of blogs. I'm sure there are other representatives from Nvidia that you can sync up with at the conference to better answer that question.
Thank you.
So why don't we start on this side over here? If you state your name and affiliation.
Hi, Christian Say from Adage. This is a question for William, relatedly, but maybe more, how much is the customization? Because you talked about a ton of customization, and so there really was a sense in which you're customizing for specific workloads, use cases in your environment. So how much was the customization? I think there's a sense that it was really to fit NVL72 into air-cooled environments. And so I'm trying to get a sense for, to what extent is it that, and fitting it into, kind of a temporary fix for fitting it into your existing heterogeneous footprint versus actual things like the CPU, GPU ratio change, these sorts of things, maybe more specific to your workloads.
Yeah, I mean, I think of the two, it is much more kind of the workload side of things. Like, we are able to make a single 72 GPU rack work with kind of a different combination of the air-assisted liquid cooling devices in our traditional data centers. It's basically something where we can kind of design to leverage a lot of the building blocks. So, like, yes, we did make changes, but there's a lot of what's kind of common across our system and NVIDIA's system. And we are able to essentially scale kind of larger and larger per rack power, working with our data center teams to essentially do kind of minor modifications within our older, more traditional data centers to help support kind of pooling power across what would have been basically many racks into a single higher power rack today. So the customizations we talked about, yes, we would have had to make slightly different design decisions at the product level if we wanted to keep within a rack, but that wasn't what drove us to make our decision.
Alan, go ahead, but state your name and affiliation.
Alan Cantle and Alisway. A couple of questions. A quick one on the racks. So we saw John's presentation of essentially slotting a 19-inch rack inside an ORV-free 21-inch rack. We heard from Google, well, we heard how Meta split that into two separate racks, and we've heard Google with their custom wide rack. And those who attended Hot Interconnects last week, we heard from Andy Beckelsstein at Arista about an ORV-free wide rack. And so I was tantalized by the Google chaps' mention of collaboration on wider racks. I was wondering if that was maybe associated with the ORV-free wide rack or not.
I'll have to check with my colleagues, but I'm fairly aware of the discussions that have started, mostly for forward-looking architectures between Google as well as our partner hyperscalers.
It would be good to get this into OCP quick sooner than later for all of us startups.
All right.
All right.
I will relay that to my colleagues. Thank you.
It's a call to action. Lots of interest out there.
And secondly, interest on the Google side again, we're seeing the continuation of a 3D torus, whereas we're seeing the scale up with a single layer of switch, like NVL72. Any comment on the Google side as to why you've stuck with 3D torus?
I cannot talk about that more in detail. All I know is, like I mentioned earlier, we look at our current generation and forward-looking workloads. We bake in as much as flexibility as possible across the entire stack, not just a scale-up network. And 3D network just works well for us.
Okay.
You should ask the question again when Norm presents tomorrow or Tuesday. Go ahead, name and affiliation, please.
Hi, this is Kenbo from SemiAnalysis. So, question for John. It is known that GB200's backplane has low reliability as of now. Do you know of any reasons to that and any plans for improving this issue on NVIDIA?
Yeah, that's definitely not something I'm going to respond to here.
It's a good question. Thanks for trying.
Yeah.
Do you have another question?
Yes, so one final question about Meta's Catalina. Does Meta have GB200 NVL72, or is it all NVL36 or 36x2?
I mean, functionally, it is a 72 GPU scale-up domain. So physically, it happens to be split across 2 racks, but you still have the same kind of connectivity where it's all of the GPUs sharing that high-speed connection. So I think, yes, I guess.
In terms of form factor, could you confirm?
I can confirm we're deploying the
single one? Is it a single 72, single rack form factor?
I can confirm we're deploying the Catalina rack. So.
Thank you.
No, I really appreciate the questions. Thanks. Nathan?
Yeah, Nathan Brookwood, Insight 64. Specifically for the Catalina guys, you mentioned that this thing was optimized for AI applications. Can you give me a few examples of the design decisions you made that were optimized for AI as opposed to general high-performance computing?
One example that we showed here was like the logging CPLDs and spread. We're much more flexible on spreading out and what would additionally consume maybe additional space, cost, power, and an AI application is something we're willing to trade off. If you look at our other OCP contributions, like the Yosemite series, they're hyper-focused on cost optimization, leveraging it, and we're kind of pushing it the other side in these complex systems. We're willing to make that trade-off of visibility and kind of connectivity.
So are there specifics like distributed, all reduced, and things like that that you've optimized as well?
I don't think we're going to be able to talk about any of kind of the workload or training specific optimizations today. I mean, I think we're dealing with a lot of the same problems everyone in the industry is. It's like, how do you get these kind of really large deployments of GPUs within a single like location where you can take advantage of the kind of high-speed interconnects that are limited by the speed of light? And so I think there's a lot of things we do to basically optimize for how can we fit as many GPUs as possible within kind of these training domains. That covers, I mean, like I talked about earlier, everything from hardware to infrastructure to software. I can't give too many more details.
Okay. The reason I asked is I've been to several conferences over the last month where people talk about AI optimization, and then when I corner the people, they say, well, the marketing guy said it's a thing that sells. And I'm just trying to understand what specific features really are tweaked for AI as opposed to high-performance computing.
Okay, so I guess Nathan wants to have lunch with you. That's a good segue. Maybe we'll end it over here.
Okay,
thank you for the audience online and in the auditorium here for your great participation, the great questions, really appreciate it. Thank you to all the presenters. They don't have to do this, they volunteer their time to put on a tutorial like this for you. Hopefully the insights were useful.